The valence electrons are the ones that are the most important in chemical bonding. Where are the valence electrons located?
The outermost.
The outermost level, the highest energy level. So they are the most loosely held. They're the ones that will get lost if electrons are going to be lost. And so it's all about the valence electrons. We're just going to completely ignore the core electrons in the Lewis model. So a Lewis symbol shows the valence electrons as dots around the element symbol. So we're going to draw the Lewis symbol for an oxygen atom. So the symbol for oxygen is a capital O. And then we need to know how many valence electrons does oxygen have? It's got 6. And how do we know that? Group number. It's in group 6A. Isn't that convenient? Let's see. I get my size right. Is that the right size? That's a good size. So 6 valence electrons. We need to put 6 dots around this. We could just kind of 1, 2, 3, 4, 5, 6. That's kind of messy and irregular, and it's also very difficult to do on a computer, and it's kind of hard to count those, right? On dice, the dots are always arranged in the same pattern, aren't they? Because once you look at them for a little bit, you realize, oh, I don't have to count the dots anymore. I can just look at the pattern and see how many there are. So what we do with these dots is we only put them in 4 positions: on the top, on the bottom, on the right, or on the left of the element symbol. So if I have 6, I might put 2 on the top and 2 on the bottom and 1 on the right and 1 on the left. And when they are in positions like that, then it's easy to count them without actually getting your finger out and counting. So we don't care exactly where, well, that's kind of a weird O. We don't care exactly where. You could do it like this. We're not going to be picky about what side they're on. But we're going to put them just on the top, the bottom, the right, or the left. So I've been drawing them in pairs, but let me show you how I would encourage you to first put them around. Just start and put 1 in each position. 1, 2, 3, 4. And now things are going to have to pair up. 5, 6. And when we do this, the number of unpaired dots here ends up matching up with the number of unpaired valence electrons in an orbital diagram. So that's kind of cool. So dots placed with a maximum of 2 per side, just an easy way to visualize what's going on. If an atom has 8 valence electrons, it's said to have an octet. Just like in singing, an octet is 8 people singing. An octet is 8 valence electrons. 8 valence electrons, as we saw from the noble gas electron configurations, is a particularly stable situation for an atom. Helium, of course, has to be an exception. It has a duet of electrons. Hydrogen's also an exception. Those are the 2 little guys. They're too small. They can't handle 8 electrons, so they're happy with 2. So the octet rule tells us that atoms transfer or share electrons to achieve an octet of valence electrons. So we've got an atom like oxygen that only has 6 valence electrons. It wants to have 8. It's not really very happy with 6. It's going to react or combine with other atoms in a way to get 8. So we'll see how that happens. So let's look at Lewis symbols for potassium and chlorine. Well, the element symbol for potassium is K. How many valence electrons does potassium have? 1. It's in group 1 on the periodic table. And the element symbol for chlorine is Cl, and how many valence electrons does it have? 7. So 1, 2, 3, 4, 5, 6, 7. So are either of these happy? Do either of them have an octet? No. What would chlorine like to have happen? It'd like to be, if it got an extra electron, then it would be a -1 ion, and it would have an octet of electrons. What would potassium like? To be +1. It would like to lose this electron. So here we have, for our convenience, the electron configuration for potassium. And here we see that it has a valence electron here, just this one. If it loses that one valence electron, then what's left to be the new valence electrons are the 3, the n equals 3 electrons. And so this is, now it has an octet in the previous level. So what potassium's going to do is it's going to say, hey, chlorine, could you take this electron off my hands? And chlorine's like, yeah, I've been looking for an extra electron. And so we just move this from one to the other. Oops. And now chlorine has an octet, potassium has an octet. It doesn't look like it does, but when you lose all your dots, what's underneath? A full shell, a full level. But there's charges involved now, right? Potassium has a positive charge, chlorine has a negative charge. I like to at least make up explanations for stuff. And usually, if I like the explanation, I don't even necessarily go looking for the true explanation. Lewis symbols of anions are written inside brackets with the charge outside the brackets. Okay, for me to remember that, I need to have some sort of a reason. If you look at this, you can imagine how a negative sign could get mixed up with dots and be kind of confusing. So my rationale for that is I want to put brackets around here to contain the dots and then the negatives on the outside, and so it's easier to see. So this is the Lewis symbol for a potassium ion, and this is the Lewis symbol for a chloride ion. Any questions? So let's use Lewis symbols to predict the formula for the compound that forms between magnesium and nitrogen. So we need to draw the Lewis symbols for magnesium and for nitrogen. So here's magnesium. How many valence electrons? 2. And we'll make nitrogen blue. How many valence electrons does nitrogen have? 5. 1, 2, 3, 4, 5. So these two are trying to come up with a way of both of them getting an octet. Magnesium wants to do that by ditching these 2 valence electrons so that it can have the complete 8 octet underneath. Nitrogen, being a nonmetal, wants to gain electrons. So they come together and they're going to help each other out. And magnesium says, here, you can have my 2 valence electrons. And nitrogen says, oh, that's awesome. This reminds me of little kids playing with Hot Wheel cars. Right? The cars come up and they talk to each other. I was never very good at that, but somehow I can make elements talk to each other. So we've got this, this electron and this electron are going to go bye-bye. They're going to go over to the nitrogen. What does that do to the charge on magnesium? It's got a 2+ charge. And nitrogen now has a charge also, right? What's its charge? 2-. Is everybody happy? No. Magnesium's happy. Nitrogen, not quite. It wants one more. What does it do? Well, if there's one magnesium atom around, there's probably another one, right? So he looks around and sees another magnesium atom. There's another magnesium atom with 2 valence electrons. Nitrogen says, hey, can I have one of those? Magnesium says, sure, take it. So get rid of this. Send it over here. So that changes the charge on the nitrogen. I'm going to get all my colors totally mixed up. It's okay. 3-. The charge on the magnesium now is +1. Nitrogen's happy. This magnesium's happy. This magnesium, no. You have to keep going until everybody's happy. It's like, man, we could go on like this forever. Actually, no, it does have an end. So The magnesium's looking around for nitrogen, somebody to take this extra electron off of its hands. So here's another nitrogen with 5 electrons, right? So the magnesium gives this electron to the nitrogen. So now this magnesium's 2+, it's happy. Awesome. Is this nitrogen happy? No. Dang. We've got 3 happy and 1 unhappy. Gotta keep going. Another magnesium atom, sorry. There's another magnesium atom. Nitrogen needs 2. This magnesium has 2. Oh, end is in sight, right? So we take those away, give them to this nitrogen. Now the nitrogen has a 3- charge, and the magnesium has a 2+ charge. And we have transferred electrons in a way that gives all of these guys an octet. The formula for this compound comes about by counting up how many people had to participate at a minimum to make this happen. Well, you've got 3 magnesiums and 2 nitrogens. And so we predict the formula to be Mg3N2. Does that make sense? This is the explanation for what we learned earlier. We learned to predict the charges of these ions. We said, well, magnesium's in group 2, it's got a 2+ charge. Nitrogen is 3 over from the noble gases, it's got a -3 charge. And then we learned to crisscross, or find the lowest common multiple of the charges and come up with this formula. This is explaining why it happens that way. Any questions? Now, we obviously wouldn't want to draw this all out every single time, right? It gets a bit tedious. So I did it once so that we understand what's going on. But normally we do just look at the charges and stick them together that way. So I said that the bonds will form if it lowers the energy. We can observe a reaction between solid sodium metal, the element, and chlorine gas to produce sodium chloride, table salt. This is a very exothermic reaction. It gives off a lot of energy. And so the heat of formation, the standard heat of formation for this is -411 kilojoules per mole. Making 1 mole of sodium chloride releases 411 kilojoules of energy. Well, we can look at the ionization energy for sodium. This is the amount of energy needed to take an electron from the sodium, because that's what's happening. The sodium is losing an electron, the chlorine is gaining an electron. So we have to give the sodium 496 kilojoules for every mole. The electron affinity for chlorine is -349. For 1 mole of chlorine atoms, if you give each of them an electron, it releases 349 kilojoules of energy. So if we add these together, we see that the transfer of an electron from sodium to chlorine actually absorbs 147 kilojoules per mole. It definitely is not releasing 411. So there must be something else going on here. Because just looking at ionization energy, electron affinity, sodium chloride shouldn't form. The rest of the story is the lattice energy. Lattice energy is the energy associated with the formation of a crystalline lattice of alternating cations and anions. And when we're looking at quantifying that, we're talking about from gaseous ions. So the potential energy of these ions is lowered when the opposite charges come together. Opposite charges attract. When the potential energy is lowered, the energy has to go somewhere, and it's usually released as heat, sometimes as light. My kids had, well, we still do, it's in the garage, a building set called magnetics. and it had these little sticks with magnets on the end and then these balls, right? And you could just build stuff and they would just like stick together through magnetism, right? That's a little bit like what happens between the oppositely charged ions in an ionic compound. They're attracted to each other. They stick together. They just naturally do that because it lowers their potential energy. So this is an important idea. The formation of ionic compounds is not exothermic because the metal wants to lose an electron and the nonmetal wants to gain an electron. I talk about it that way. I will continue to talk about it that way because it helps us to remember and think about what's going on. But that's not what drives the reaction. There's a large amount of heat released when the cation and the anion come together to form a solid. The opposites being attracted releases energy, and that's what drives the formation of ionic compounds. Any questions? Now let's try to make sense of this crazy picture. So this is an artist's illustration or attempt at illustrating what happens when you've got chloride ions and sodium ions that were in a gas state and now they're coming together. So this is just, I can't do it on the screen. This is just like shooting in towards each other. They're all attracted. Well, chloride ions are not attracted to other chloride ions, but they are attracted to sodium ions. And so what happens is they will naturally arrange themselves to maximize the attractions and minimize the repulsions. So we see that we have a sodium ion next to chloride ions. And the chloride ion is surrounded by sodium ions. So we've got positive, negative, positive, negative, positive, negative. And the amount of heat released when that happens is the lattice energy. It's kind of like when there's this attraction between two people, right? And they come together and there's all this heat generated. Interpret that however you want.
So the lattice energy is heat, but it's not exothermic.
It is exothermic. So the lattice energy comes from the lowering of the potential energy. These particles just floating around have a higher potential energy. When they come together, the energy is lower. That energy has to go somewhere, and that's the energy that's released. Because what we observe is that sodium and chlorine reacting to form sodium chloride is a very exothermic reaction. But we can't explain it just looking at, well, sodium wants to lose an electron and chlorine wants to gain one. That still gives us a positive number saying you'd have to put energy in. The reason that this is negative is that when those ions come together, they release a lot of energy. Their potential energy is lowered.
So we don't take into account those energies,
Well, we're going to look at that. Right here, we're just showing you these numbers to illustrate that that's not the explanation, not the whole explanation. So how would you calculate this lattice energy? Well, believe it or not, the easiest way is through what's called a Born-Haber cycle. So this is a hypothetical set series of reactions or steps that represent the formation of ionic compound from its constituent elements. And this is based on Hess's law. These processes are state functions. So they don't depend on how it happens, they just depend on where it starts and where it ends up. So we can make up a hypothetical series of steps to get from the atoms to the ionic compound, and it doesn't matter if that's actually how it happens or not. But we're going to do a series of steps where we know the energies. And these calculations are not going to be exact, but they're going to be pretty good, and it beats trying to actually measure it in the lab, which can be extremely difficult. So we're going to use steps where we know the standard heat of formation for the different things that we're looking at. We also need to know the overall change in enthalpy. So we need to know the heat of reaction. For sodium and chlorine, it was the minus 411. And so we're going to compare that to the series of steps. And the difference, the unexplained part, is the lattice energy. So this requires some explaining. So what we've got here is a diagram where as we're going up, energy is increasing, or enthalpy is increasing. And so we kind of have to look around and orient ourselves. Here's our starting point, the elements, sodium and chlorine. They're going to react and form sodium chloride. The reason that the sodium chloride is shown lower is because this is an exothermic process. So we know the standard heat of formation for sodium chloride. You can look it up in a table. What we don't know is how much of that is from this lattice energy. So what we're going to do is we're going to make this happen in a series of steps. So we're going to take sodium, solid, and make it into sodium in the gas state. And that's the formation of gaseous sodium from solid sodium, and that can be measured. And then we're going to take this chlorine molecule and break it apart into chlorine atoms, and that can be measured. And then we're going to ionize the sodium, so make it into an ion. And then we're going to make the chlorine into an ion. This one goes down because that's exothermic. All of these other steps were all positive. And so we can add up step 1, 2, 3, and 4 and compare that to this. And it's just like going up in elevation, going up 1, up 1, up 1, up 1, and then down a half. And then this is the difference, and that's the lattice energy. Yes?
Is this a lab reactor for checking?
We are not going to do this as a lab, no. Be cool, but it's really, really complicated. We're just going to do this on paper. A lot of this is someone else has already studied all of these processes and measured them and tabulated them. That's why that CRC, I don't know where it went. It went to the other room. The CRC is big, thick book, right? That's all stuff that people have measured and put into tables, and so you can just go look those numbers up. So if you want to know the lattice energy of sodium chloride, you can look up these things and add them together and get your lattice energy. So there are trends in lattice energies, and it has to do with ion size and also with the charges of the ions. So here in this table, we're looking at metal chlorides: lithium chloride, sodium chloride, potassium chloride, cesium chloride. These metals are all alkali metals in group 1. And if we compare their lattice energies, we see that as we're going down in this group, the lattice energy is becoming less negative. So negative lattice energy means a lot of energy is being released, and this smaller negative means less energy is being released. So why is it decreasing? It has to do with the size of the ions. So here's an illustration of their sizes. So we're comparing chlorides, so we're keeping the anion constant. But look at the cations. We learned in chapter 8 that as you go down a group, the atom or ion size is going to get larger, right? So think about cesium, big ion, trying to get close to chloride. The distance between the nuclei is going to be 348 picometers. Lithium is a little ion. Its nucleus can get closer. And so the distance here is 241 picometers. The lattice energy depends on how close those ions can get to each other. You got a big old bulky ion, it just can't get in as close. It's like, somebody wearing one of those inflated suits. You know, you might not even be able to get close enough to the other person in the sumo suit to even kiss or something, right? It was just a big, bulky thing, right? So this one's not wearing the big, bulky suit. It can get in closer. Coulomb's law, remember, was E equals bunch of junk, but basically 1 over r, right? So the energy is proportional to 1 over r, the radius, the distance between these. So if the distance is larger, the attraction is less. The lattice energy will be less. Does that make sense? Think about a refrigerator magnet, right? The distance between the refrigerator magnet and the refrigerator itself is going to affect how well that magnet, or how strongly the magnet's attracted. You can try this at home. So you stick the magnet on there, it sticks real well. Stick a piece of paper under it. Stick another piece of paper, another piece of paper. You'll get to a point where just one more piece of paper and now the whole thing is starting to slide down because it's just not attracted as much. It's very sensitive to the distance between. Ion charge also has an effect. So here we're going to compare sodium fluoride to calcium oxide. We chose these two to compare because the distances between the nuclei in these compounds are going to be similar. Okay, this distance will be 231, that one's 239. We know that distance affects the lattice energy, so we want to try to control that and just look at different charges. Sodium is +1, fluoride's -1. Calcium's +2, oxygen is -2. Well, Coulomb's law, energy is proportional to Q1 times Q2. So if Q1 and Q2 are larger, then the energy is larger. So this is 1 times 1, and this is 2 times 2, or 4. So that predicts that this would be 4 times as attracted. And look at -910 and -3,414. So just out of curiosity, what's 4 times 910? 3,640. Ballpark, about 4 times as big. That make sense? So the charge, higher charges will be more attracted, meaning the lattice energy will be greater. Smaller ions can get closer together, and so lattice energy will be greater. That works with people. So you got two people are attracted to each other. Well, if they're, the charges are greater, they're more attracted to each other, there's going to be more heat, given off. If they're both wearing sumo suits and they can't get close to each other, then there's going to be less heat. If they're wearing, bathing suits, they can get really, really close. I don't know. Does that work for you guys? Whatever helps you remember. I try to keep it PG at least in here, but whatever. So summary of the trends. Lattice energies become less exothermic, smaller, as the ionic radius increases, and they become more exothermic, larger negative, with increasing magnitude of charge. So we should be able to predict relative lattice energies, just looking at the periodic table. So here they're asking us to look at lithium bromide, potassium iodide, and calcium oxide. These are kind of like those logic puzzles that some people like to do. So lithium is +1, and bromide is -1, and potassium is +1, and iodide is -1, and then calcium is +2, and oxygen is -2. You got to think about the charges. You can really only compare 2 things at a time. So I approach a problem like this, I'm like, well, this pair and this pair are both +1 and -1. So the charge isn't changing. I'm going to look at size to see which one's bigger. So looking at sizes, here's lithium and here's potassium. Which one's bigger? Potassium's bigger. Let's look at the anions. Here I've got bromide and iodide. Which one's bigger? Iodide. So in the potassium iodide, we have larger ions, is that going to make for more attraction or less attraction? Less. So that's going to be lower lattice energy. Lower lattice energy. So I'm supposed to arrange these in order of increasing. So if I do these two, I'm going to have lithium bromide is lower in lattice energy. Nope. Is higher in lattice energy than Ki. Did I do that right? So now let's compare calcium oxide to one of these. Well, these have higher charges, right? Is that going to make higher lattice energy or lower? Higher. Okay? Higher charges, higher attraction. So I want to compare this to the higher one here. So we also have to think about sizes, right? So calcium and lithium. So here's calcium and there's lithium. Calcium's bigger. And then I've got oxygen and I've got bromine, and bromine's bigger. So in lithium bromide, one of them's bigger, but one of them's smaller than in calcium oxide. And I can't quantify that based on the periodic table. But maybe the distance between them is like roughly the same. It's certainly not clearly different like here, where potassium's bigger than lithium and iodide's bigger than bromide. Clearly this one has a larger radius, a larger distance. Does that make sense? So the calcium oxide is going to have a higher lattice energy than the lithium bromide because the charges are greater. Right? Because the energy is proportional to Q1, Q2 divided by R. So here we've gone from Q1, Q2 for lithium bromide is 1, plus 1, and minus 1. For calcium oxide, it's 4. That's going to overcome quite a bit of difference in the R. Any questions? So we've talked about this model of ionic bonding. Does it match up with what we observe? Because that's the ultimate test. Does it predict? Does it explain reality? What we observe for ionic compounds. Ionic compounds have high melting points. Well, in an ionic compound, we have attractions in multiple directions. So the high melting point is due to these non-directional bonds and bonds in all directions, and that's holding it together more tightly than, say, a covalent bond. We see that ionic solids are non-conductive. So these ions in the solid are fixed in place. The ions have to move in order for electricity to be conducted. If we put this solid, see here's the solid, no conductivity. If we put it in a liquid, if we dissolve it and make a solution, now it does conduct. Because the ions separate from each other, they are soluble, they're soluble, and so then they can move. We also see that if you melt sodium chloride, it's conductive. Because in the liquid state, the ions can move. Yes? Say what again? The melting point. Okay. So a high melting point. In order for a substance to melt, it has to go from this rigid, fixed condition to where the particles can move relative to each other. So it takes a certain amount of energy to separate these. The higher the melting point, the more strongly those things are held together. And so because these bonds are non-directional, they're in all directions, they're going to be stronger than if they were not. We're going to talk a lot more about melting points and how that's affected. Right now, we're really just focusing on does it explain, and it does.